your first quizzes are graded, and they're now in STARS subsystem as quiz grades for first quiz grades. And I have the papers for them. So on the 10-minute break, you can look at them. You can also keep your quizzes, like you can take them. But if you have any questions about grading, like I saw many people got 5, and some people already told me they were expecting more. You can write an email to the assistant and ask for particular grading policies. So all the decisions about grading are made by the grader. Okay? So you should discuss with him about grading. Okay. Other than that, today we will do permutations and combinations. This is one of the important sections for this course. So we in general we call it counting, but it's the permutations and combinations. These are the things that gives the name combinatorics to this subject. I prefer to call it counting because you will see that the main idea is to learn how to count certain sets in a suitable way. Now, we had 2 rules that I wrote last time. I'm not going to repeat them, but just write what they are. The rule of sum, and then we had the rule of product. These are 2 main principles for counting. So using set notation, the rule of sum is basically you're trying to count union of 2 sets, but you know these sets have no intersection. So you conclude that the number of things in this union is exactly sum of the number of things on each set. So basically, if you have a union of 2 sets, the number of things in this set is sum of in each set if you have no intersection. Okay? But in word problems, this comes up as summing cases. We actually did some examples of this last week, and I guess on Tuesday too, where you had situations you were supposed to find number of ways to distribute, say, candies, where the youngest child gets 1 or 2 candy. So you first count the ones which you give 1 candy to your youngest children, and then you count the ones you give 2 candy to the youngest child, and then you sum the situation to find all the cases, all the situations where the youngest one gets 1 or 2 candy. So this is a typical case where you count each set and add them up. This is called like counting cases. And it's strictly in this setup because a youngest child cannot get 1 and 2 candy at the same time. You either get 1 or 2 candy, right? So you don't have intersections. You'll see later that when you have intersections, you need more sophisticated counting methods. That will be called inclusion-exclusion principle. And we will devote quite a bit of time to understand how you count union of sets when you have intersections. But this is the most basic situation where you have no intersection. Now, the rule of the product is essentially counting Cartesian product of sets. But we usually draw it in this picture. So you have some procedure or experiment with R steps. So you have first step, second step, and so on, and Rth step. And this procedure has this property. This is also very, very important, that on each of these outputs of the first step, you have exactly the same number of output for the second step. So this uniformity, that these number of outputs being equal, is a very special thing. It doesn't happen all the time. Actually, one of the biggest misuses of this rule is not seeing that the outputs actually have different second level outputs. So you have to make sure before you use this rule that each output has the exact same number of outputs in the next step. Okay? So if this is the case, say this happens all the way to here, and again, independent from what happens before, on each output here, you have exact same number of outputs. Okay? If this is the case, then what you do is you count the number of outputs on each step and say this is N1, this is N2, number of ways to do this, and then NR, and you say the number of ways to do this procedure is exactly the product. Okay, so this is the number of outcomes, is the product of these things. And these numbers are number of ways to do each step. And this is just a nested tree algorithm, and it's very easy to see why this is the case. But this rule of product is also a very important rule. And these two rules gives you pretty much all the counting problems you will face. Let me start some examples. In examples, we'll see how to use these rules, and we will develop the concept called permutations and combinations using these procedures. So the first question is just a word problem. The drama club of Century University is holding tryouts for a spring play with 6 men and 8 women. Auditioning for the leading role, leading male and female roles. In how many ways the director can cast this leading couple, the leading couple. So we have 6 men and 8 women, and we need to choose a leading couple, like a male and a female, for the leading roles. In how many ways this can be done? Any answers? 48. So you're saying that the answer will be these product of these things. Okay. So let me explain using procedures. You can think this is 2-step experiment, right? In your first step, you can say choose the leading male. Okay, so choosing the leading male is your first step. And this step, as you can see, there are 6 men. This can be done in 6 different ways. And independently from who you choose, your second step is choosing the leading woman. And this step, again, independent from what happened in this first step, can be done in 8 different ways. You can choose any of the 8 women. Okay? Choosing a man in certain person doesn't affect your choices in the second one. This is completely independent, two steps of your experiment. Because of that, you can apply product rule and conclude that it is 48. Okay? Now, this is the most easy case. You can see the product rule. We'll do more sophisticated examples. But unfortunately, what happens is that when you go into further and further sophistication on these things, the simple things get sometimes lost. For example, many of you will be tempted to divide this by 2. Why shouldn't I divide by 2? I know many of you will do it in the future. Try to divide by 2 because they will think it's symmetric. Divide by 2 because we choose the man first, the woman first, 2 different things, so I divide by 2. Why do I not divide by 2? Why we don't divide by 2?
Order doesn't matter.
Order does or does not? Order of the... I mean, it does actually matter, the order in some ways, but in other ways doesn't. I mean, you're choosing the male role, okay? So you're not choosing just arbitrary something. So you could, by choice, say, I am going to choose the male role first. And this does not violate anything about your choices. You're exactly choosing all the possible pairs by first choosing the males. It doesn't hurt your choices, okay? So by this way, we are always choosing male and the female, and we don't have to divide by 2 because males are different than females. If I were choosing 2 people out of 10, then I could choose them in different orders. But here, I have males and females are different. So I could choose the males first with no problem. Okay? But just start thinking about these kind of random divisions is one of the evils of this section. Many of you will do random divisions, random multiplications by 2. Those things, they should all depend on some rule, some idea, something. You should not randomly multiply or divide by numbers. There should always be reasoning behind everything you do. Here, there is no need to division because product rule clearly says if you do this way, you get 48. And there is no division in this. Okay. Just a warning. Some of these things get a little fussy when you go a little further in the course. Let's do another one. So this is actually an example of permutation. In a class of 10 students, 5 are to be chosen. And seated in a row for a picture. How many such linear arrangements are possible? So that means how many different pictures can be taken with the order of students being different. 10 factorial, I have 5. Huh? Over 5 factorial. Okay, so solution is, first we haven't learned the factorials yet, so let me write it in normal way. So you're suggesting that it's this number, is that? How many people agrees? Yeah. Any other? Do we have other answers? Like this times something? Okay. Any ideas why we get this number or how we can get this? Do you agree with the number, or you think it's not too big?
For example, if
Uh-huh.
you change the students'
Uh-huh.
place, but same students,
Uh-huh.
does it count as same or?
No, it counts like a different picture. So if say 5 of the front row here, 5 students, if you switch you two on the picture, that's a different picture.
Then, I think
Then this is it.
some
Okay. So when it says linear arrangements, that means that order is important, like how the people are. If we were choosing, which we will do in a few minutes, if we were choosing 5 students to form a committee or to put them in a bag, then order wouldn't matter. But here, the order matters. So the first student on the left is important. So you're saying that this is also should be multiplied with this. Everyone uses factorial, so let me say what factorial means, then we can use it, because I have to formally introduce it. Okay, so for a positive integer n, the n factorial is defined as, so this is the notation, n with a dot is this product of all numbers less than n. And by convention, we also define 0 factorial as, just to make it easy for us, and 0 factor is always 1. Okay, so these two numbers, you are suggesting 10 factorial here. So, and then this first suggestion is this, because you chop out the 5. So which one is more correct? Or we could have a third choice too. Dennis, which one you think is correct? First one. Maybe we should take votes. How many people think first one is correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Admit it, 20 people think this is correct. So how many people think 2 is correct? 2. Okay. Seems like... Okay, the first one is correct. And we're not going to even think too hard. We're just going to write it in such a way that it will be... I mean, once I finish writing why it's that, it should not give you any hesitation that why is the answer. So the aim of this section is to do combinations, permutations in such a way that anytime you write a solution to a question, anybody reading it will know exactly why that answer is that. So writing this is not solving a question, right? You just wrote some answer. So solving a question in this section always will mean to write it in such a way that anybody who not sure about it becomes sure about why your answer is correct. So how do we solve it? So these are answers, now solutions. And let's try to write a solution. So the solution, we have to use one of the rules, right? there's no really addition here because we're trying to get some linear arrangements, which means there's a multiple process. So we can actually set up a, we can consider this as a 5-step procedure, right? Where your first step is choosing student to put on the most left place. So now if you want to put 5 people in a row, we lost one of them, but if you want to put 5 people in a row to take a picture, you say, oh, I have 10 students here, let me choose one of them to put on the most left place first, right? So it's like you need to put someone in the most left. So the first step is actually choosing student to be on the most left. Okay? Choosing a student for the most left spot. Right? You need to choose someone to be on the most left spot. That's your first step to do. You need to do this. Without this, you can't line them up. Once you do this, your second step will be independent from who you choose, to choose another student to put next to that student. Choose a second student to stand next to the first student. And independent from how many ways you do this, you will have exactly the same number of ways to do this. Because it doesn't matter who you choose as a first student, as long as there's no restrictions like somebody don't want to be next to someone and so on. The second student can be chosen independently from the results of the first experiment, first step. Okay? I can actually start putting numbers too. How many ways you can do the first step? 10. You have 10 students. They're all different. They have names and they're all different, right? So you need to choose one of them. And this can be done 10 different ways. Right? Now, if you choose Ahmed, Mehmet, and Esra, and so on, it doesn't matter who you choose. You have same number of choices for the second step. What's that number of choices for the second step? 9. Because you already chose one student, you have 9 left to choose from. So for the second step, you have 9 choices. Note that I am doing this I will be doing this 5 steps, right? So on the next one, will be 8 left. So we'll have the third student, 7 left, because there will be 7 students left, and 6 left. Okay? For the fifth location. And the product rule says you can do this in product of these many ways. Now, when you multiply this, you're finding number of tuples, basically, where the first spot is one student, second one another student, this one is a student, this one, and you do this in such a way that the order matter, because this was the first spot. So you already choose the student with the arrangement that is going to go to the first place. So this one of these choices is already ordered. Okay? Like if you finish say this step, you will see that the first student E, Serkan, Murat, Hatice, and Taner. So this will mean that you have Esra, Serkan, Murat, Hatice, and Taner. That point is exactly that. So it's already ordered, which means you don't need to multiply with arrangements anymore, right? It's already ordered. Any questions on? You understand this point will always mean that this is the order, this is the arrangement. So the answer is the product of these. Okay? Any hesitation that it could be different? You're counting number of ES and HTs, basically. We will have questions where we'll be choosing, like you'll be ordering from a menu, where you'll be ordering different food items and different pizzas and so on. And there will be varieties where not the things you're choosing are identical. So this is actually a very special case where students are all distinct. So this is a case where you are choosing things, you already know they're distinct from each other. So it will matter later if things you're choosing from are distinct things or not. They will be, like you'll be dealing with distributing 10 identical candies to 3 students. How you do this? And there will be different questions. So the language here is distinct and identical. Okay. So here students are distinct. That's why we did this way. If they weren't distinct, if this was candies, if the distribution was different, you cannot use the product rule anymore. Okay. I mean, the product rule works because they're all distinct and there are different steps and so on. So many special things goes together to make this solution correct. Now, this is actually more general than just choosing 10 out of 5 in a row. This is a formula that you can write as a permutation formula. So imagine that you're dealing with this in a more general sense, that you have n distinct objects and you want to put all of these in a line, in a linear order. So if there are n distinct objects and R is an integer with somewhere in between, then the number of permutations permutations means linear orders, different linear orders. So you're putting them in a line of size. Size is the length of the linear order, size R for the n objects is. So the notation is P and R, which we won't be using as much, but just know that it's P and R. And so what do you expect the formula to be? Let's write it. So you'll be, first step will be n times. This is your second step. You'll have one less person to choose from. This is your third step. You'll have one less. And you'll be doing R many times. So you will go all the way to n minus R plus 1. Because the first one is n minus 0. So this is your formula. And because you go all the way to the n minus r plus 1, you're actually missing the next one, which is n minus r. So you can also write this factorial divided by factorial, right? So how can you write it as factorial divided by factorial? N factorial divided by? No. N minus r factor. That's important. So if you were choosing 10 out of, maybe I shouldn't have used 5, but if you're using 3 out of 10, it will be only 3 terms here. So that means you will be dividing to 7 factorial, right? So if you're choosing 10 and 3 people out of 10, this is 10 times 9 times 8, but that is 10 factorial divided by 7 factorial. So 7 is n minus r. Okay? You're not dividing by r factorial. This is just actually, I will suggest never use this because this is too complicated. Just multiply r many times by going down by 1 each step. That's the way to memorize it, because each step you're choosing a student n different ways, n minus 1 different ways. You have to do it r times. So just memorize it this way, or try to understand it as this formula, not as a formula like that. So this is your first formula, permutations. We'll do combinations as well, but maybe in a few minutes. Let me do one question. These are all from Grimaldi. You can read them later if you want again. So the number, how many different words are different 8-letter words one can form using the letters of computer. I should have used electronics maybe. This is chosen because the computer science students were taking it at the time. So I thought that would be appropriate. But there's also a reason for choosing computer. It's an 8-letter word. Maybe let's make it 8, and then we can drop it if you want. So how many different 8-letter words one can form from computer? 8 factorial. So solution, it is 8 factorial because we're doing combinations. This is the permutations because it's the permutations. Every permutation, this is the number of permutations. Permutations of 8 distinct objects into linear arrangements of length 8. I mean, this 8 choose 8. So this is actually 8 choose 8, right? P88. This is why it's that. But we got lucky here because all the letters are distinct. The most famous questions of this form is not with computer, but you replace this with some other thing. I can never pronounce it. Masasa Uga. So same question with Masasa Uga becomes a different problem. Why it will be a different problem? Yeah, there's some of the letters are same. There's some letters repeats. So to deal with letters that repeats, you have to have a different strategy because now they're not all distinct. So to deal with situations where you have repetition, you need to, we'll be using something almost like combinations, not permutations, but combinations. But to come to that, I'll do a very easy question first, so that it becomes more natural for you to understand what the formulas are. But as you see, our analysis here stops when you start having repetitions. Okay, so we have to do something different. So far we have done permutations where everything was distinct and it worked, but as soon as you have some repetitions, not distinct things, it doesn't work anymore. So the most easy example where I can explain this situation is this question. So what is the number of arrangements of the 4 letters in ball? So if they were all distinct, you'll be having 4 factorial, right? Which is 24. But we expect that it's not going to be 4 factorial. Anybody knows what the answer? 12, half of it, right? So if they were all different, we'll be having 4 choices, 3 choices, 2 choices, 1 choice. Will be 4 factorial, so 24. But the suggestion is that it's actually 12. So somewhere you're dividing. You're dividing the whole situation to half. Okay? This is the first time you see a division situation. So division situations are actually things that comes from product rule again, but product rule in a backward way. So I'll explain why it is half of what you will have if they were all distinct by using product rule again. Okay, so stay with me. Let me solve this using the product rule, and then we'll make it a rule later, and you don't have to write this way each time. So suppose that we were facing letters. We were arranging the word E, A, L1 and L2. Suppose that we have L1 and L2 instead of just LL. Okay. Then number of ways to arrange it. So you use the product rule to get the arrangement like we did before. Like choose the first letter, choose the first one, choose second one, third one, and fourth one. Right? And each step you're choosing something. So that's where you get the 4 factorial. But the letters we're looking for is not subscribed, like there is no 1 and 2. So this arrangement with the 1 and 2, you can visualize it also as a 2-step experiment, where you're in the first step, you're arranging the letters for ball. So these are arrange the letters for in ball. And the second step, choose subscripts for these letters. Okay, second step, choose subscripts for else. Let me write a table here so that you see what's going on. So on the left side, you have this 4-step procedure where you have sort of B, A, L1, L2. So you're arranging B, L1, L2, and then each of these you can do, this is 4 different ways, and each of these choices you have 3 choices, here you have 2 choices, here 1 choice. Now suppose your choice were here B. Here you have 3 choices left. Say you choose L1. Here you choose A. Here you choose L2. So what you have here, B L1, A L2. This is one of the words you can find. So these are the ones with L1, L2 arrangements. Each of these is a ordered BL1, A, L2. Now I'm saying something we want to know, which we don't know, is here. This is the number of arrangements of all the number of arrangements for BLR. So arrangements, arrange B, A, L, L. So each of these is now an arrangement of these things. So one of them is B, L, A, L. This one B, A, B, say L, L. And all of them are just arrangements. And each of these arrangements, because they are identical L's, you have a second step where you decorate these L's. Okay? So this is decorating L's. So in this one, for example, you have 2 different ways to decorate your L's. You could say, okay, I want this decoration, or I can this decoration. Always 2 different ways of decorating your L's. For example, here, one of them is B L1 A L2. The other one is B L2 A L. But at the end, what you get on this here is same as the list here. For example, this one is here as this one. So number of outcomes of this experiment is same as outcomes of this experiment. They're identical. You may wonder why I'm spending so much time on something. It may look very just divide by 2. But if you understand this in these easier cases, you can use the same method in very complicated questions. This is the heart of the matter, that everything is product rule. If you understand this, then you don't need to worry about any hard question. All the questions will be just variations of this. Okay, so what we are facing here is this is the number of ways to count all these arrangements of BL1, BAL1, L2. We wanted to know all the arrangements of ball, which we don't know. And then we found that there is a second step I can add to this, where everything has 2 different ways of proceeding. I get this. So this number should be equal to question times 2. So because of that, now you know your question. Your question, what you want to know is this divided by 2. So your answer for ball is 4 factorial divided by 2. It's actually 2 factorial by 2. So it's 12, which we expected. But you see, I mean, there's always a good reason to divide. If you divide, you have to explain it, why you're dividing. I'm trying to avoid you in the future face a question and randomly write some numbers and multiply them and divide with some numbers and say that's the solution. So it's never going to be like that. There will be more complicated questions, and the answer is never going to be just writing products of numbers. It's always going to be some procedure that you have to explain why it comes like that. So try to get used to this idea that even you divide by 2, you have to explain why you're dividing by 2 so that you don't randomly, mistakenly divide by 2. Okay? That's the whole idea. So at the end, it was dividing by 2 because we're over counting. We are counting too many permutations where L and L are actually identical. We just shouldn't be counting their switches. That's why we're dividing by 2. You can think that way too. Okay? But this gives you a new formula called combinations. Let me write it. But before doing that, let me write this. So we get this formula. You can actually make it a little bit more elaborate. If there are n objects with n1 indistinguishable identical objects of a first type and 2 indistinguishable objects of a second type, and are indistinguishable objects of art type, then there are n factorial divided by n1 factorial and 2 factorial r factorial arrangements of the given n objects. So this is your formula. This is going to be the formula you use for Masasauga. Masasauga. I know I'm going a little over time, but let me show you how you use this. Now I can talk about it. So this is 10. Onu çıkardık. Masa sağ. 8 olursa zor olur. Yapamayız. Sadece buna bakalım. Şimdi, now you're in a position to answer this question using this formula. Each of these divisions, think about putting subscripts underneath things. So, for example, A's, you can think of A1, A2, A3, A4. S's, S1, S2, S3. So you can actually explain it by product rule. So what should be the answer? Huh? 10 factorial. You have 10 letters, so it should be 10 factorial. Divide by. So you have 1 amps, 1, 2, 3, 4 amps, 4 A's, 3 S's, and 1 U's, and 1 G's. Right? So you have to put a factory for each of them. One factor is already 1, so you can put it there, but it won't count. So it's actually 10 factorial divided by 4 factorial times 3 factorial. And the reasoning behind this, again, the same product rule, you put subscripts for these, so you can do this 4 factorial ways, subscripts for this, 3 factorial different ways. So you have to divide by these to make it even. That's the idea. Okay, let's take a break. I'll continue in the second time.